to part 2 of the tutorial by Tropp. So.
All right. Welcome back. Thank you for your continued interest. So let me remind you quickly about what we're doing and where we've come from, and then I'll tell you a little bit about where we're going. So this lecture series is about randomized algorithms for matrix computations. And the way I've organized this is by identifying themes, which are different ways that you can use probability to design linear algebra algorithms. And for each one of these themes, I've tried to identify a couple examples of how you can use this idea to solve different linear algebra problems, several linear algebra problems. So last time, we started out with Monte Carlo approximation. So what's Monte Carlo approximation? In its simplest form, the idea is that we are going to identify a simple, unbiased estimator for a quantity of interest and average independent copies to reduce the variance. Okay, so we saw two examples of the Monte Carlo approximation approach. The first one was implicit trace estimation, where we saw that quadratic forms with random vectors can give us an unbiased estimate of the trace, and by averaging together several of these simple estimates, we can reduce the variability of the estimator. And it was surprising, perhaps, to see that with only a constant number of these quadratic form evaluations, we can estimate the trace of a positive semi-definite matrix up to a relative accuracy with good probability. So that was cool. We also saw another example of approximate matrix multiplication where we averaged together some randomly chosen products of individual columns of the matrix to get an approximation for the entire product. And we saw that if you're multiplying a very fat matrix by a very tall matrix, that the cost of approximating this product actually doesn't depend on the inner dimension. You can always approximate it accurately, even if the inner dimension is like a trillion with a number of products that only depends on the outer dimension, the little one. Okay, great. So those are two examples of Monte Carlo approximation. Today we're going to move on to a different theme, which is random initialization. So what is random initialization? The basic idea is that, as you know, the progress of an iterative algorithm depends on the starting point. Oh, sorry, quick comment. The lecture notes for this entire short course are available at Archive, and I'm following these notes, and the notes have details that I'm not putting on the board. If you find any mistakes, let me know. I will fix them. Okay, so the progress of an iterative algorithm depends on the starting point, and the hope is that by choosing a random starting point, to encourage a favorable trajectory. All right, so many of you are optimizers. Can you think of examples of how this plays out in optimization?
Gradient descent.
Yeah, so how does that work?
If you start close to the optimizer, or to the optimum, you don't need too many descent steps to get there.
Yeah, all right, and the hope is that if you start at some random place,
Might take a while.
well, yeah, so let me draw a picture of a paradigm that is often called random optimization. So here's what random optimization looks like in 2 dimensions. So we've got a landscape of some objective function, which has isocontours and maybe looks something like this. And your goal is to find a minimizer of this function. So It's a complicated function. It's got a complicated landscape. We don't know what to do. So maybe we'll start by dropping a random point here and doing a local search. And then this local search maybe wanders off this direction, doesn't give us anything useful. OK, let's try again. Now maybe we start here. And now our local search approach tends to this local minimizer. So maybe that's good progress. We try again. Maybe this time we land here, and the local search takes us down here to the global optimizer within this frame, and that makes us happy. So by comparing the objective values at the endpoint of each of these trajectories of the local search, maybe we can find a good outcome. Okay. As you can imagine, this is a little unreliable. You're basically like blindfolded and you're throwing darts. So not necessarily any reason to believe you'll land close to the local minimizers, but if you put down enough points, you're likely to find something reasonable if the dimension isn't too high. Okay, so let me just write down what we've done here. For nonlinear programming, we start local search methods at a random point in the hope of landing near a minimizer. Okay. Now, it is also true that for a lot of kinds of functions, you are guaranteed that gradient descent started at a local minimizer tends toward the gradient descent at a random point will converge to a local minimizer. So that's something. The question, in some sense, is really how many local minimizers there are, how spread out they are, whether you can actually get near them. Okay. Now, in linear algebra, the situation is actually a lot simpler because the landscapes tend to be simpler because the problems are all linear or convex or have strong duality or something like that. So we're going to look at two examples in numerical linear algebra today. The first one is finding the maximum eigenvalue, which is one of the problems that we started out with as an example of how you could use randomness in linear algebra. And so I'd like to dive deeper today, and I'd like to show you in some detail, which I hope is not too excruciating, why a random initialization is important and how it helps ensure that you can estimate the maximum eigenvalue efficiently. Okay, so here's the setup. We're going to let A be a real, symmetric, positive semi-definite matrix. So again, just to keep things simple, with eigenvalues and eigenvectors, lambda 1, v1, lambda 2, v2, and so forth, down to lambda n, vn, and by our positivity assumption, these eigenvalues are all real and non-negative. Okay, now we're going to be interested once again in the model where we access the matrix via matrix vector products. So given an input x, we can compute the output ax. Okay? So we access the matrix via matrix vector products. And our goal is to approximate lambda 1 with the fewest vex possible. Okay. So once again, we're treating this as the primitive. We pay every time we perform this operation, but we don't inquire into its internal complexity. Okay. So there are lots of situations where this happens. In classical applied math settings, the matrix might be the discretization of a differential or integral operator, and it's very natural to think about the action of those operators on vectors. In more data science applications, you might think about A as being like a Gram matrix or something, where you don't want to write that product explicitly, you would rather perform the product in 2 steps. AX, then A star times AX, something like that. So there are lots of settings where it behooves you to think about this as the primitive and to count these operations. And generally from a computer architecture perspective, the more matrix you can make the primitive steps in your algorithm, the faster the algorithm is going to be on modern computers. So it's really better to think about this rather than trying to mess around with the entries of the matrix. And matrix products are even better if you can get them. So put a pin in that for later. And let's talk about this problem. So any ideas how to solve this? Yeah?
Just pick a vector at random and then just multiply by a.
Yeah. So what's that algorithm called?
Power method.
This is called the power method. So this is a very classic algorithm which has been made newly famous by PageRank. So here's how the power method works. I'm going to be more detailed this time than I was last time. So we're going to let omega in Rn be a starting vector. And I'm going to set the initial iterate x naught equal to the starting vector. I like to distinguish where we start from the sequence of iterates. And at each step, we're going to compute a vector qt by normalizing the current vector xt. These are Euclidean norms. And then we make a new iterate by multiplying q into a. T equals 0, 1, 2. And how do we get an eigenvalue estimate from this? We compute xt equal to qt inner product with xt plus 1, which has this explicit form. So it's the quadratic form in qt. Because qt is always normalized, this is a Rayleigh quotient. Okay? So this is our eigenvalue estimate. And we'd like to understand what xt does. How does it compare with lambda 1? How many steps do we need to take to do something reasonable and so forth? Okay. Any questions on the statement of the algorithm? Okay. So this normalization is very important in practice because it helps keep things from blowing up and helps preserve stability. So this is a pretty typical set of steps for an implementation of this method. Now, what's the intuition here? So if you unroll this iteration, you'll see that qt is the tth power of a times the starting vector divided by its norm. Okay. So what's happening here is every time we multiply, we accumulate another copy of the power, and we can just collect all the normalizations together. Okay? So the reason this is helpful is that if you look at the matrix a to the t divided by its spectral norm, this matrix can be written in coordinates using an eigenvalue decomposition. So we've got lambda I divided by lambda 1 to the t power times vi times vi transpose. So let's forget about the normalization for a minute. The tth power of a raises the eigenvalues of a to the tth power, and it leaves the eigenvectors alone. Okay? And that's because these are all orthonormal. This is easy to check. And when we normalize by the spectral norm of a to the t, well, this matrix is positive, so the spectral norm is lambda 1 to the t power, and so we've got that normalization here. Okay? So all of these numbers are smaller than 1. What happens as we increment t? We're driving these numbers to, well, we're driving some of them to 0, and some of them stay at 1 forever. Okay? So this thing here converges to the orthogonal projector onto the leading eigenspace. Okay? So for simplicity, you might think about lambda 1 as being a simple eigenvalue, in which case we only have the first term in this sum, the lambda 1 term in the limit, and everything else goes to 0. Okay? If it happens that the first eigenvalue is multiple, you might get a projector onto a higher dimensional space. So be a little careful about that. Now, the point is that because this matrix drives toward the projector onto the leading eigenspace, eventually that's all that's left here. And so QT will be aligned in the leading eigenspace, and that's it. Okay, there won't be anything else. And so we will have found an eigenvector whose eigenvalue is maximal. So that's the intuition. That makes sense? All right, I hope many of you have seen this before. All right, so that's the idea about how it works. We'd like to quantify this, and we're going to be more careful about that in a minute. Okay, good. Any questions about the statement of the power method or this intuition? Yeah?
Should it be AT plus 1? In the intuition QT, should it be AT?
QT.
Oh, sorry.
No, I
QT,
think
QT.
I think
Okay,
it's
okay.
right. I think it's right. Yeah. Okay, cool. Anything else? Yeah.
Could you explain one more time
Mm-hmm.
how, like, in the final step where you basically ended up with this quantity a to the t divided by the spectral norm of a to the t? Like, where was the, what was? Can you unpack that step a little more?
Yep. Here's what's happening. Every time we take a step of the power method, we multiply by another copy of a.
Right.
You can ignore the scaling because the product's linear, right? So every time we multiply, we accumulate another power of a to the 1, a to the 2, a to the 3, okay? And so the number of a's matches the degree of q, the index on q. So qt, a to the t.
Yeah.
Got it?
Yeah.
Then we normalize by whatever the norm is,
That's good.
and that's it.
Okay, but for the final
Wait,
step,
where, here?
Yeah, like
Oh,
defining the
I'm sorry.
spectral norm of a
Oh,
to the t.
sorry, I misunderstood your
Okay.
question. So the a to the t is lambda I to the t time blah, blah, blah. So the spectral norm is the largest eigenvalue of that matrix in magnitude, and so that's a lambda 1 to the t, and so that's lambda 1 to the t here. Is that the part you were asking about? Or it was the next step?
I think the question was how you go from QT equals this, and then the next line just you lose the omegas, right?
Oh, yeah, this is a separate comment. So this is what QT looks like. It is a matrix A that is driving omega, and then the question is, what does that matrix look like?
Got it.
It looks like an orthoprojector. That's the idea.
Right.
Yeah.
What happens if you start with one of the other eigenvectors?
Oh, well, that's bad news, isn't it? Yeah. Great point. So we're going to quantify this in a second. Yeah. And this is indeed where the randomness comes in. Okay, good. More questions? Okay, right. So use the whole board today. So we're going to measure the error in approximating the maximum eigenvalue in the relative sense. So we're going to define the error in CT to be lambda 1 minus CT divided by CT. CT is always smaller than lambda 1 because it's a Rayleigh quotient. Okay? So this is always a positive number. All right? And, oops, sorry, lambda 1 in the bottom, not CT. Sorry. And so this is a number between 0 and 1. It's a relative measure of how well we've done. And we would like to understand what happens to the relative error in estimating the maximum eigenvalue as we proceed with this algorithm. OK, so the classical analysis in its simplest form is essentially what I showed you already, but I'm going to be a little bit more careful, and we're going to have a look at this relative error and see what happens to it. We need to stare at it a little bit to understand what's going on in this algorithm. So we're going to assume from now on that lambda 1 is equal to 1. And this is just a normalization that will help us simplify formulas. So long as A is not a 0 matrix, we can always rescale it this way. Okay? And because we're talking about relative errors, we don't care about the scaling. Okay, so good. Now, we're going to write the starting vector in the eigenvector basis, which is a natural thing to do in a linear algebra problem. So what do we mean here? We're going to write omega is the sum from I equals 1 to n of omega I, vi, with omega I defined to be the inner product between vi and omega. Okay, so omega I are the coordinates in the eigenvector basis. Again, very natural for a linear algebra problem. Okay, and this is going to help us understand what's going on. All right, good. So now we're going to look at this formula for the relative error, and we're going to write it in coordinates. So write relative error in coordinates. So how does this work? So the error in CT is 1 minus QT transpose AQT. So this is the definition of CT. We've used the fact that lambda 1 is 1 because we've rescaled. Now, we can write 1 as in this rather obscure form, minus this quantity so all I've done here is taken the formula for CT. I have introduced the expression for QT here. So that gives us omega transpose A to the T. The A and the A to the T combine to give us an extra power. And then we have the normalization. For the first term, you can see there's one smaller power of A here. And I've just written this in a clever way so it looks like the thing on the right. So this is equal to 1, but we've found a common denominator. OK, so this isn't so interesting. Let's continue with the calculation. So now we're just going to combine these terms. So we have omega transpose A to the 2t. So these t's combine. We've got an identity minus A, because here we have a 2t power, and here we have an extra power of A. And we've got an omega here. So we have this quadratic form divided by A to the t, omega squared. Fine. So again, We have an identity because there are 2t copies of A here. And we have an extra A because there are 2t plus 1 copies. And now I'm going to write this all out in coordinates using the eigenvector basis. And I'm going to get the following formula, which I'll try and write big enough for everyone to read. So we've got omega I squared, which comes from these two guys. We've got lambda I to the 2t, the ith eigenvalue of this matrix, to the 2t power. We've got 1 minus lambda I. And all of this is divided by the sum from I equals 1 to n, omega I squared, lambda I to the 2t. So this is an expansion of this in the eigenvector basis. Okay. So if you haven't followed all the details of the calculation, this is not so important. The important thing is that we have wound up here at this expression, and we're going to need to understand what's happening here. Okay, let me pause and ask if there are any questions that I can clarify before we move forward.
So the second term, I think the denominator should have also a square, right?
Yeah.
Oh, absolutely, for sure. Thank you. Yes. Good. More questions? All right, great. So now the thing I'd like to do next is use this formula to prove the classic result on convergence of the power method. And you'll see how this formula feeds into this analysis. And this will help us understand why randomness is important. So we're going to assume that A is not 0. And we'll assume also that the first coordinate of the starting vector in the eigenvector basis is not 0. And the claim here is that the error in the tth eigenvalue estimate converges to 0 as t goes to infinity. So in other words, if we run this algorithm long enough, it will eventually converge to the correct maximum eigenvalue under the sole condition that the first coordinate of the starting vector in the eigenvector basis is not 0. All right. Good. Any questions on the statement of this result? Okay, so here's a sketch of the proof. If A is equal to the identity, this is a trivial result. Otherwise, we're going to let M be the multiplicity of the maximum eigenvalue. So what does that mean? It means that 1 is equal to lambda 1 is equal to lambda 2 is equal to lambda m, which is strictly bigger than lambda m plus 1. All right. Now, I'm going to write out this formula to expose the role of the multiplicity. So in the numerator, what happens? So some of these eigenvalues are equal to 1, and what effect do they have? Yeah, so for the first m coordinates, this term is 0, and so it goes away. So we can start this sum at m plus 1, and I'll write all this stuff out. And what happens in the basement? Well, for I equals 1 up to m, these guys all equal 1. So there's nothing interesting happening here. So I'm going to pull all those out. So we have omega 1 squared up to omega m squared plus the other terms, sum I greater than m, omega I squared, lambda I to the 2t. And now we're in a good position. I realize these formulas are a little bit messy, but I'm going to try and help you focus your attention on the parts that are important. So we've assumed that omega 1 is not 0. So that means this parenthesis here is not equal to 0. Now, what happens to these other terms? What do we know about lambda I for I bigger than m? Smaller than 1. So what happens when you exponentiate it? Okay, so these guys go to 0. And that means that this term and this term both tend to 0 as t goes to infinity. But this term's not 0. Okay, so we don't have to worry about, like, a vacuous form and L'Hopital, all of that nonsense. This whole thing converges to 0 because we have something here in the basement to anchor it. Okay, and that comes from our assumption that omega 1 is not equal to 0. Okay? Any questions on this argument? Okay, you can make a stronger claim now, which is that, in fact, the starting vector better have a non-zero coordinate in one direction in the leading eigenspace if you want this to work. This speaks to your question. If this is false, the algorithm will converge to the wrong place, guaranteed. Okay? This is necessary and sufficient if the first eigenvalue is simple, and there's a natural extension if it's not simple. Okay? Questions about this? All right, so we've seen how important it is that omega 1 is not equal to 0 here. And now, I don't think I need this anymore. So, the question, of course, is how can we ensure this? So here's the thing. Do you know the eigenvector basis of A? If you did, you'd be finished, right? There would be nothing to compute. So you can't assume what you're trying to find is at your disposal. And so it's a little bit tricky to pick omega 1 not equal to 0 when you don't know what direction this is. So of course, what is the natural remedy altogether?
Can you start with some other basis?
With some what?
Can you just start with any other basis?
What do you mean?
Start with n initial vectors that form a basis.
Yeah.
And run them all in parallel.
Yeah, you could. Yeah, but you need a full basis, right? So that's expensive, right? Because if you leave even one guy out and you happen to be wrong, that's an interesting strategy, though. Okay, so what could we do if we don't want to do that? We're going to pick it at random altogether. Okay, so idea, pick omega at random. So this is a very old idea. If you look in old linear algebra books from the, I think even from the 60s, you'll see that there is a proposal that you might think about doing this, although they wring their hands a little. As I said, linear algebra computation researchers historically did not like randomness very much. So what distribution do we want to use? Yeah, it should be supported everywhere. Yeah, isotropic's actually not quite enough. There's something else that we want to take advantage of. So the eigenvectors of a symmetric matrix form an orthonormal basis. Okay, but we don't know what directions those are, whether it's this way or this way. And so we want to choose a distribution that's indifferent to the choice of basis. So these distributions are called rotationally invariant. So we need a rotationally invariant distribution. Do you know some rotationally invariant distributions? Yeah, we're going to pick a Gaussian. And the reason that we can pick a Gaussian among all the rotationally invariant distributions is that the power method is scale invariant. The first step is to normalize. So we are going to choose the starting vector, x, omega, is omega, to be normal with mean 0 and covariance identity. And the key fact is that omega 1 up to omega n, the coordinates of omega, are IID normal 0, 1 random variables, regardless of the choice of the eigenvector basis. Okay, so this is amazing. So you don't know the eigenvector basis. You picked this beautiful random vector, and the coordinates in whatever the eigenvector basis are still standard normal, and they're independent from each other. Okay, so this is exciting. You somehow have gotten something for nothing. All right. Now, as a consequence, an immediate consequence, we see that with probability 1, CT converges to, actually, let me just write it this way. The error in the maximum eigenvalue converges to 0. Why is that true? It's because with probability 1, this standard normal vector variable is not 0. So we can activate this proposition. Okay? So with probability 1, omega 1 is not 0, and therefore the power method converges with this choice of a random start. So you can find this in lots of linear algebra textbooks. Maybe they're not so explicit about the role of the normal distribution, but this is something that's been known for decades at least. And the power method is actually roughly 100 years old. It was introduced by von Mises and Muntz in separate work. It goes back a long way. All right, now the question that I would like to talk about now is how fast does it converge? And we're going to talk about some results in this direction, which really heavily exploit the distribution of omega. And the key fact is that when you look at this formula for the error, typically, how big is omega I squared? Well, the variance is 1, the mean 0. So omega I squared is about equal to 1. So heuristically, for a standard normal, you would expect this formula to hold with omega I equal to 1 in all these places. Okay? And that's more or less what happens. The analysis is a little bit more complicated than that. But I want to emphasize two things that are going on here before we continue. The first one is that we really need omega 1. Let's look at this version of the formula. We really need omega 1 to be bounded away from 0 to help anchor the denominator. So that's one good thing that the Gaussian gets us. Omega 1 is probably not too close to 0. The other thing that we want is that these other omega i's are also not too close. The other thing we want is that these other omega i's are not too big. Otherwise, the numerator is big, and that drives the error up. So the fact that omega 2 up to omega n are all kind of small helps us ensure that the numerator isn't huge. Okay? So we get both of those things from this distribution. This guy is not too small. This guy is not too big. All right? And if we don't know the eigenvector basis to begin with, this is kind of the best we can do. This is something you can prove. Okay, great. Any questions on this? Okay, so let me write down the first theorem, and we'll talk a little bit about this. Okay. Randomized power method with a spectral gap. So as you may know, classical analyses of the power method always assume that the leading eigenvalue is separated from the second eigenvalue, or maybe the third or the fourth or something like that. And we're going to argue that in this case, the expected relative error in the eigenvalue estimate is at most the square root of 2n times lambda 2 divided by lambda 1 to the t power. And this is valid for t equals 0, 1, 2, and so forth. So under the assumption that there's a gap between the two eigenvalues, we're going to get it bound on the expectation of the relative error. Now, the size of the relative error depends on the gap. And it's more convenient to rewrite this in terms of the relative spectral gap, which is lambda 1 minus lambda 2 divided by lambda 1. So for the relative spectral gap, the error is bounded by root 2n times e to the minus gamma t. So the spectral gap tells us the rate of convergence, which is exponential. So in the presence of a spectral gap, the power method converges to the maximum eigenvalue exponentially fast at a rate determined by the spectral gap on average. I'm not going to talk about probabilities because they just cloud the situation. This is a very good description of what happens in practice, even though it's just a mean. Okay? So, any questions on the statement? All right, let me say another word about how to understand this. So suppose that you want relative error smaller than epsilon. So to get the expectation of the relative error less than or equal to epsilon, it suffices that the number of iterations t is bigger than the log of root 2n plus the log of 1 over epsilon divided by gamma. So what this tells us is that if you plot the relative error as a function of the number of iterations, what happens is that the relative error doesn't do anything for a while, and then it starts to decay exponentially fast. Actually, let's do this on a log scale, sorry. That'll be clearer. So log of the relative error, here's 0, this goes on. So for a while, the relative error does this, and then it starts converging linearly. So there's a burn-in period of about log root 2n steps when nothing happens. So for a while, the relative error is vacuous. And then it starts to go down linearly. And the slope of this line is gamma, the spectral gap. Okay? So you find out both that there is a burn-in period before the algorithm does anything, and you find out that it converges at an exponential rate determined by the spectral gap. Okay? So this is actually more or less classical, but the sort of elegant form here will depend on the random model. Okay. So any questions on the statement of the result before we talk a little bit about how to prove this? Okay. So beautiful fact. And this is actually necessary in general, this burn-in period. You actually need log n steps for the worst case problems to get a non-trivial estimate of the maximum eigenvalue. So this is actually a result due to Arcadi. Okay, so here's a sketch of the proof. It depends on the following fact. The expectation over a standard normal variable of c over g squared plus c is less than or equal to the square root of pi over 2 times c. So for g standard normal, you can compute this integral and get this lovely bound. Okay, so here's the proof sketch. We're interested in the expected relative error. And we're going to compute the expectation in 2 steps. We are going to first average over, need more space. We are going to first average over omega 1, and then we're going to average after that over omega 2 up to omega n. Why can we do this? It's because they're statistically independent. Because we started with a standard normal distribution. It's actually the unique rotationally invariant distribution with that property. And what does the error bound look like? Okay, well, we're going to notice that lambda 1 is equal to 1. So the first term here goes away. So we have the sum from I greater than 1, omega I squared, lambda I to the 2t. And this number is always smaller than 1, so I'm just going to get rid of it. Okay? I used it to kill the first term in the sum, and then I don't need it anymore. In the basement, I'm going to pull off the first term, omega 1 squared, which has a 1 attached to it. Omega 1 squared. And now I have the sum from I greater than 1 of omega I squared, lambda I to the 2t. Okay, so this is just a simplification of my exact formula for the relative error, where I've made some estimates. And by the independence of the coordinates, I can compute the expectation in 2 steps. Okay, well, look here. This is standard normal. Here's the square. We've got the same number here in the numerator and the denominator. So we can apply this fact to get the expectation of omega 2 up to omega n square root pi over 2 times the sum I greater than 1 omega I squared lambda I to the 2t. Okay? So one of the other beautiful things about this is that because we have this exact distribution, we can look this up in, I don't know, Abramowitz and Stegen or something, which is what I did. Great. What do we do now? Well, is there something else in the denominator that I could apply this idea to? No, there's no denominator anymore, right? So what kind of function is the square root? It's concave. So what do I do with an expectation of a concave function? We're going to Jensen this. All right, so this is less than or equal to the square root of pi over 2, sum from I greater than 1, expectation omega I squared, lambda I to the 2t. Oh, that's 1. And now I just need to clean up. So I'm going to bound the rest of these guys by lambda 2. I'm going to count the number of terms in the sum. And I'm going to obtain the bound root pi over 2 times n minus 1 times lambda I to the t, sorry, lambda 2 to the t. And then this is smaller than root 2n, and because lambda 1 was equal to 1, I can just stick it back in here because this whole thing is scale invariant. Okay? So that's a proof of this theorem about the convergence of the random power method with a spectral gap. And again, what I want to emphasize is we've taken advantage of two things. The fact that omega 1 is bounded away from 0, and because it has this standard normal distribution, we can compute this expectation exactly and then make a simple estimate. We're also taking advantage of the fact that the other coordinates, which are independent, are all about 1. And so these two things are important. The starting vector should be somewhat aligned with the leading eigen direction, which is ensured, which ensures that this is under control. And it should be not too aligned with the other eigen directions, which keeps this from blowing up. And so that's the idea here. Okay. Any questions on this? Yeah.
So if you had a multiplicity of greater than 1 in the top
Yeah.
eigenvalue, it would improve the condition.
Oh, yes. It improves it dramatically. So you get a significantly better rate if the multiplicity is 2. And for multiplicity 3 and higher, it gets even better. So roughly, if the multiplicity is 3 and higher, you get an extra factor of 2 here. This is kind of amazing. But you can't be sure that that happens. And in fact, most matrices maybe don't have multiple eigenvalues. So, okay, more questions? Okay, I want to tell you about another theorem now, which is random power method without a spectral gap. And in some sense, what I've just showed you is something that you can extract from the classical analysis of the power method. This other result that I'm about to show you, which depends on probability, seems to be something that was discovered in the early 90s. I really should have mentioned that this proof is one that I developed, but it's based on a paper by Kuczynski and Wozniakowski from 1992, which is absolutely remarkable. But they compute integrals over the unit sphere, which is a nightmare. Whereas if you use Gaussians, you can do it on one panel of the board. Okay, so Kuczynski and Wozniakowski also established a result without assuming a spectral gap. And to the best of my knowledge, there is actually no classical analog for this result. So for non-zero PSD matrix A of dimension n, the expected error in the maximum eigenvalue estimate is less than or equal to 1 plus log root 2n plus log t divided by t for t equals 1, 2, 3, and so forth. And in particular, to get a relative error on average that is smaller than epsilon, we need t to be bigger than 1 plus log root 2n plus log t divided by epsilon. So if you compare this result with the one that I just erased, so that was bad manners, sorry, you see that there's still a burn-in period. You need about log n steps before anything happens. And now the convergence is polynomial in epsilon. Okay, so if you want to get down to error epsilon, you need 1 over epsilon steps. So that is much worse than the log 1 over epsilon we saw before. On the other hand, what's vanished? The spectral gap. This is true for every matrix, regardless of whether the top 2 eigenvalues are separated. Okay? So let me repeat that. This is true without any assumptions on the eigenvalues of A. Whereas the classical results all seem to require the spectral gap to produce anything. And so it was discovered in the early 80s and then elaborated in the early 90s that, in fact, if you exploit the randomness in the starting vector, you can get a convergence result for any matrix with any eigenvalues. So it's an incredible feature that comes from the probability. Yeah.
Sorry, I'm confused.
Mm-hmm.
If lambda 1 is equal to lambda 2, then you can just use the version of that result that allows for multiplicity, right? So what do you mean by there's no gap?
Yeah, that's a great point. So the problem is the gap could be very, very small. So you could think that lambda 1 and lambda 2 are different, but they're 10 to the minus 11 apart or something, in which case you get exponential convergence with a rate of 10 to the minus 11th, which is glacial. Yeah, it's geologic. Whereas here, all right, it's slow, but there are no assumptions. So this is what happens when the eigenvalues might coalesce, okay, or are very close to each other. And this happens a lot, actually. There are lots of problems where the eigenvalues are close, and nevertheless, you get a result. Yeah.
The algorithm is not changed. You're doing the same algorithm?
Same algorithm. Yeah, the algorithm didn't change. It's just the analysis. So I'm not going to prove this result for you. It's mostly the same as this, but you have to split the sum here depending on the size of the lambda I. You put the big ones in one batch, you put the small ones in another batch, and then you optimize for the split. So I don't want to talk about the details. It's not so interesting. Okay, so to recap, the reason that the power method works with a random starting vector is that the random starting vector is somewhat aligned with the leading eigenspace, and it is not so aligned with any of the other eigenspaces. And those two features together give you this convergence behavior, either with a spectral gap, as in this case, or without a spectral gap in this case. And to the best of my knowledge, this analysis with the random starting vector is the first one that detected this property that the power method works even without assuming a difference in the eigenvalues. Okay? Good. So we're going to take a break now for 15 minutes, and then the second part of the lecture will be shorter. We will talk about the randomized SVD. Okay. Thank you.